There we go. So we're live. We're going to be finding the distance from a point to a line, and we're going to do it in 2 dimensions. And we're also going to do it in 3 dimensions. Okay, 3 dimensions, there's another dimension. So that presents its own unique difficulties. We're going to look at the 3-dimensional example that we could have applied to the 2-dimensional example, but you're going to get an idea how we can use different things like dot products and normal vectors and projections in algebra to tell us things that we want to know. All right, so here's my line. 5x plus y plus 8 equals 0. So I've got the scalar form of the line. This is 2 space. There's only an x and y. And I have a point out here, q, negative 4 and 3. What I want to know is how far away is q from this line? And when we're talking about distance from a line or distance from a point to a line, we're always talking about the perpendicular distance, right? Because that's the one that's going to define a single distance. Okay. What's nice is this is a perpendicular distance, and so that's related to which vector? The normal vector. Yes, the normal or orthogonal vector. This is in scalar form. Who can tell me what the normal vector, a normal vector to this line? If you said 5 and 1, that's right. So when we have the scalar equation, we can actually just read off those coefficients, and that tells us the normal vector, okay? You cannot read that off if it happens to be in y equals mx plus b form, okay? Or if you're looking at it, in vector form or something like that. Okay, there we go. So there's a normal vector there, okay? I need to find this distance. There's no really handy way to do it. There is a way I could use the dot product. We're going to use a method by which we project one vector onto the normal vector to find out what the distance is, okay? So if I just have a point out here, any old point, which I'm going to call P naught, and I'm going to call this point that is the shortest distance to P, I'm going to call this one P up here, okay? I can find this vector, QP, or the magnitude of this distance, by projecting this vector, QP naught, onto QP, okay? So the projection of QP naught onto QP is going to be this distance, okay? So I'm just projecting. In other words, I'm just finding a magnitude. All right. I can choose any old point that I want to figure out what QP is, okay? So let's see. If I choose 0 for x, so let's choose a 0 for x. I put a 0 in for x. 0 plus y plus 8 is equal to 0. So if I put a 0 in for x, I get out a negative 8 for y out of that. So this is my point P down here. Now I'm going to have to turn QP into an algebraic vector so that I can project it. So I need to do the old tip minus tail. Okay, so this is the tip. 0 minus negative 4. So there's the x component of QP. And negative 8 minus 3. And so QP as an algebraic vector is 4, negative 11. Okay, so I found out what the x and y components of vector QP are. And I did it by taking the tip, so the coordinates of the tip, and subtracting the coordinates of the tail. So I took the x part of P here and subtracted that, and I took the y part of P here, and I subtracted that. So now I have QP in algebraic form, and I'm all ready to use my projection formula that was really just the dot product, okay? So the projection of QP onto, QP naught onto QP, or the magnitude of the projection, is just equal to QP dot n, and then this is all over the magnitude of the normal vector. Okay, so all I have to do is 4, negative 11 dot the normal vector, a normal vector, 5, 1, and then I have to divide that by the magnitude of the normal vector. And so the magnitude of the normal vector, we just have to use our Pythagorean theorem. So this is 5 squared plus 1 squared, which is going to make square root of 26. Okay, so let's do the dot product of the top. 4 times 5 is 20 plus negative 11 times 1. And so the top ends up being 20 minus 11. So 9 over square root of 26. So just 9 over root 26 is the magnitude of the projection of QP naught onto QP. And if you really get nerdy about it, we rationalize the denominator sometimes. And so this is 9 root 26 over 26 in nice old school format. Okay, so that last step is just tidying it up.
So like you had 20 minus negative 11. Then where'd you go?
Okay, 20 minus negative 11. Sorry, 20 plus negative 11 is 9.
So why is it plus?
That's how I calculate the dot product. 4 times 5 plus negative 11 times 1. Okay? And I get 9. All right, that's the magnitude of the projection. So that's just the projection of a vector onto another vector. That gives us the magnitude, but not direction. That's the size, so that's the distance. All right. Are you ready to go into 3 dimensions? Johnny, are you all ready? By no, I know that you kids mean yes. So here we go. Same idea, okay? We have a line in 3 space, and we have a point in 3 space. Now, what's a little bit different about 3 space is just the fact that there is no unique normal. So we cannot use this technique to find out what the distance from the point to the line is. So we've got to switch it up a bit. Here we go. We're just going to look at, believe it or not, a line and a point. A line and a point are enough to define a plane. And so we can just flatten this out on the blackboard and it's going to be just fine. So here's my cue. I need 3 coordinates now because I'm in 3 dimensions. So this is going to be 4, negative 1, and 1. Okay. And my line, I'm going to write it out here in parametric form just because that's going to be handy when we get around to it. X is equal to 1 plus 2t. Y is equal to 3 minus t. And Z is equal to negative 1 plus t. All right. There it is in parametric form. What would this be if I wrote it in vector form? So instead, X, Y, and Z. And I have a position vector plus some parameter. In this case, it's t times a direction vector. What would I? 1, 3, negative 1, and 2, negative 1, and 1. Yeah, there we go. So that's it in vector form. Okay. Which one is the direction vector? Because we're going to use it in a minute. Second one, yeah. Okay, so this is my direction vector over here. 2, negative 1, 1. So that's important to keep in mind. This is a position vector, so 1, 3, negative 1 lies somewhere out on this line, and that's going to come into play a little bit later. All right. I do not know if I had a perpendicular line that went from here to the line. It would be super nice to have that, and then it would intersect at a nice point that has coordinates x, y, and z. Okay. Gee, that would be nice if I could find that. So here we go. We know the direction vector could be put on that line and it would run through that line. Okay. We also know that this line would be perpendicular to the direction vector. So if I do the dot product, what should it be equal to? 0. Yeah. So the dot product of the direction vector with the dot product of this algebraic vector should be 0. So let's set that up. We can actually get this so that we express everything in terms of one parameter, t. If we solve for that parameter, we're going to be able to find out what point this is, x, y, z. Okay, all right. So first of all, we need to do QP, and so we're going to do tip minus tail. Okay. Is everybody ready? Yeah, that's right. So we're doing x, y, z minus 4, negative 1, and 1. Okay, so we're going to find QP. It's going to be equal to x, y, z minus 4, negative 1, 1. All right. But look, let's express x, y, and z as in parametric form so that we get this down just to one. We get this down to one variable. So this is 1 plus 2t, 3 minus t, and negative 1 plus t minus 4, negative 1, 1. Okay. 1 plus 2t minus 4 is negative 3 plus 2t. I know that this is my relationship, right? Yeah, so this is x, y, and z expressed parametrically in terms of one variable. So as long as I know what my t is, it tells me any point on this line. So I'm going to find this particular point. I'm going to find what value of t gives me this particular point by putting it into the dot product and making it equal to 0. Okay, good. So where were we? We were 3 minus t minus 4, and so this is going to be negative 1 minus t. Okay. Ooh, my t's are turning into little pluses here. All right. And this is negative 1 plus t minus 1, so this is negative 2 plus t. Okay. So there's my vector QP expressed in algebraic form. I'm going to go over here. So QP dot d has to be equal to 0. Yeah, so it's tip minus tail. Okay. So this x is 1 plus 2t. So, oh yeah, it is. Look at that. Thank you, Morgan. That is a negative 3. Yep. Okay. We're good so far? Okay. Negative 3 plus 2t. Let's see. Oh, 3 minus negative 1 should be 4. Yeah. 4 minus t. Beautiful. Good. Did it on purpose. Okay. That means I've got to fix this. You guys causing all kinds of problems. Okay. 4 minus t and negative 2 plus t. And now I'm going to dot product this with my direction vector, which is 2, negative 1, and 1. And this whole thing has to be equal to 0. Look, I'm going to get this down to a single parameter. Okay, so this is negative 6 plus 4t. So I did the dot product there. Plus negative 4 plus t. Okay, so I did the dot product here. Negative 1 times 4 minus t. Now I'm going to do 1 times negative 2 plus t. So this becomes negative 2 plus t. And that whole thing is equal to 0. So this is the direction vector here. We do not use it again because this is just the direction vector, and to get anywhere on the line, we'd be multiplying it by t. So yeah, we don't need the t the second time. This is just a vector, and when we do the dot product with it, it should all be equal to 0. Okay, good. When I solve that, t is equal to 2. All right. I now can calculate x, y, and z just by substituting a 2 in here. Okay?
How did you get the
Yeah, you just solve for t. So you're just doing the algebra required. Okay, so let's figure out what my x, y, and z is. So p, my x coordinate is 5 because t is 2. Y, so t is 2 is 1. And z, t is 2, and so it's 1 as well. So my point here is 5, 1, 1.
Did you just put 2 back in the X, Y, Z?
I just substituted the 2 back in here for t, okay? And I calculate my x, y, and z. So hopefully I've done that right. Okay, I found the point that is, when I connect Q to P, it's perpendicular to the line. Now, normally the question is, what is the distance from Q to the line? And so basically I have to find the magnitude of QP. So I need to figure out what QP is as a Cartesian vector and then just do the magnitude, okay? So the magnitude of QP, oh, let's just do QP all by itself first, and then we'll find its magnitude. So I have to do the tip minus the tail. So QP as a Cartesian vector is 5 minus 4, it's 1. And then 1 minus negative 1, so it's 2. And then 1 minus 1 is 0.
What are you trying to find?
I'm trying to find QP as an algebraic vector. So I have a point here in 3 space. I have a point here in 3 space. I just need to find the vector that gets me from one to the other. No, we just do the tip minus the tail. So 5 minus 4, 1 minus negative 1, and 1 minus 1. And that tells us what that is as an algebraic vector, okay? So there's QP, magnitude of QP. I'm going to do the 3-dimensional Pythagorean theorem, okay? There we go. That is the distance from Q to P, okay? This is probably the trick that you're going to use most often. Shouldn't it be negative 2? It's 1 minus negative 1. In the end, it doesn't make much difference because I'm doing negative 2 squared. All right, so there's the magnitude of QP, square root of 5. So we did that by taking our parametric equation of the line, okay, just choosing, trying to figure out what the value of t was. It was going to give us the point that was perpendicular between QP and the line. And then finding out what t was, plopping t in to find out what the point was, and then figuring out how long that vector was, okay? All right, last thing that we're going to do. There is, by the way, another technique that we're not going to go over today, but I could just pick any old point out here, right? So I could choose the position vector, for example, and I could project this vector onto the direction vector to find out what the magnitude of this side is here. And if I know the magnitude of this side, then this being a right angled triangle, I could figure out what the distance is that way. Okay, so I could have done that. That is actually more work, and this dot product system is more efficient. You could have done exactly the same thing in 2 space here. All right, so let's do this one more time. No, we're not going to do that. We're going to do the parallelogram one. Okay, so we can use the parallelogram approach for this, and we're going to do it mostly because it just reminds us about the cross product. Okay, so if I have a point here and I have my direction vector here, okay, so here's my direction vector. Any old point will do, and we go out here to Q again. Okay, Remember, this forms the basis for a parallelogram. Okay. And what's nice about a parallelogram is we use the height to figure out the area. What's also nice about these vectors in two space, okay, it's just the fact that when we do the cross product, we get the area of the parallelogram. Okay, so the area of the parallelogram is two things. And so here's our point P naught out here. So it is cross product of PQ. And if I just use my direction vector along here, it's cross product of PQ and the direction vector. Okay, so that's the area of the parallelogram. Also, the area of the parallelogram can be expressed as magnitude of the direction vector, in other words, the base, and times this height. So we're just going back to grade 9. It can actually be the magnitude, the distance, the length of the base, times the height, which is the perpendicular distance from the line to Q. So we've got two ways that we can calculate the area. All we have to do is just plunk it into the two formulas and away we go. Okay. So, in other words, here we go. PQ. I am going to choose the point on the line that is just basically the position vector. Okay, so you've got the position vector written down, and it was 1, 3, and -1. I am guaranteed that that point lies on the line. Okay, so PQ, we are just going to, or QP, doesn't matter which one we do. We're just going to figure out what that is. I chose this point because it is the position vector for this line. I know that this point lies on the line for sure, because this is the position vector for that line, right? So the position vector comes out to the line from the origin. So this point definitely lies on the line. Yes. So do you remember we went back and we had the parametric version of the line, and then we put together the position vector plus t times the direction vector. Okay. So this was the position vector from way up. Okay. All right. Good. So PQ, tip minus tail, 4 minus 3 is 1. Okay. -1 minus 3 is -4. And 1 minus -1 is 2. Very good. And we're going to cross product that with our direction vector. Okay. What was our direction vector? Oh, it was 2, -1, and 1. There we go. Okay. So cross product. We don't actually have to do the cross product here. In other words, do the sample calculation. This comes out to -2, 1, and 5. So yeah, so cross product, I'll do it in a, yeah, you have to set it up, so it's a lot of work. Okay. All right. And then the magnitude here is equal to the square root of -2 squared. Uh-oh, I hope everybody can see. Plus 1 plus 25. And so this is 26, 30. So this is the square root of 30. The magnitude of the cross product is square root of 30. That is the area of my parallelogram. Okay, square root of 30. Now I need to find the magnitude of the direction vector. Okay, and I'm just going to use this good old square root 2 squared plus -1 squared plus 1 squared. Okay, times my h, and I don't know what my h is yet. So this is square root of 30, and this is 4 plus 1 plus 1. This is square root of 6 times h. So h, isolating, is equal to the square root of 30 divided by the square root of 6. And just so we remember from grade, gee, I don't know if this is a grade 12 thing. Square root of 30 divided by the square root of 6 is the same as the square root of 30 divided by 6, which is the same as the square root of 5, which was what we got for h last time. Okay, that's that.